right, ladies and gentlemen, thanks for joining me today. I especially want to welcome all the representatives of our competitors who would like to hear about how we tackle the scalability and efficiency of electrolysis power electronics. And I hope it's over there. Then we'll just continue. So if you're looking at the challenges that you have with rectifiers, always good to first take a look at the cost of green hydrogen. As we're in the Netherlands, I've taken an example of the Netherlands, offshore wind, and how the cost is distributed. And obviously, most of it, as with a lot of other cases in green hydrogen, is simply the cost of the electricity. But also a few other things. CapEx is still considerable, and a large proportion is also the grid fee. So, two obvious questions are, what are the effects of the rectifier efficiency on OPEX, but also on CapEx? And instead of paying for the grid, can you actually get paid as an end user? So moving into the efficiency first, I try to visualize the flow of, or the effects that each conversion step has. So let me explain. Ideal case, if you want to make a certain amount of hydrogen, ideally your stack has 100% efficiency, your converter has 100% efficiency, so therefore you would only need a certain amount of electricity. You do have to take into account, however, that to feed an electrolyzer for 100%, you typically need at least twice the amount of renewable energy sources. So if you have 1 megawatt of electrolyzer, you need about 2 megawatts of installed capacity of solar and wind, as a rule of thumb. So what happens then if you look at an actual typical case with a stack efficiency of about 75% and a converter efficiency of about 95%, which is typical for thyristors, and with IGBTs slightly more efficient than that. And then you see that the inefficiencies act actually as a leverage multiplier. So it's not just a few percent that you're losing in the rectifier. It's more than doubled because you have this stack up of inefficiencies that you have to compensate for in the installed base of your renewable energy sources. Now, just to give you an example, by just increasing converter efficiency to 98%, you already see that this leverage is visible. So instead of just a few percent, so going from 5% loss to 2% loss, 3% difference, you see that on the feed-in, the difference is actually quite larger. On the whole grand scheme of things, it's still not huge, but the cost effect on the CapEx of the PV or wind that you need to install in order to get to a certain amount of hydrogen, that does make a big dent in your upfront investment. So it's not just about savings on the OPEX, so the electricity cost, but it's certainly also on the CapEx. And if you look at the feed-in, that's one point, but of course also on system level, if you're making less heat, your cooling system can also decrease in size. So on a system level, the impact is actually quite larger than just looking at the efficiency per se. So another aspect in power electronics is the grid connection. 3 parts play a role here. So harmonics is one. So total harmonic distortion is basically the difference between the grid current and the sinusoidal wave that you would expect ideally in an undisturbed grid. So if you want to have an installation that works at scale, and we'll come back to that, you definitely need to be as close as possible to this sinusoidal wave on the input side of the converter. Another part is the power factor. That's the ratio between real power and apparent power. So basically it's this phase shift between the voltage and the current. Ideally, that's overlapping. So then power factor is 1. And on the output side of the electrolyzer, you also have the DC, so direct current, where the ripple is of influence on the lifetime of the stack. But that's a minor point. Going back to the grid connection and the power factor, So it's all about proportionality. You see now a lot of projects that are in the 10, maybe 20, 50 megawatt range. That's already quite big. And then we're just a nuisance to the grid. And sorry for still using a coal power factory as an example, but it's still mainly the truth around the world. So at that scale, we're just a nuisance. If you scale up to 100 megawatts, to gigawatts, then we're really starting to get noticed by the grid operator. And at a gigawatt and up, we are actually the grid. So the disturbances that you inject into the grid are of a major importance. So if you think that by having a 10 megawatt project, and that works fine, that you can immediately scale that up to a gigawatt without taking total harmonic distortion into account, you're sadly mistaken, unfortunately. So it's something you really have to take care about. So if you look at old school technology, so thyristors, in order to get to a sort of sinusoidal waveform, you really need a lot of hardware next to the thyristor converter. And this hardware also has very long lead times. So to even make it work at scale, you need that hardware. And actually, you don't need to. There's a lot of technology now that can actually stabilize the grid rather than disrupt it. And that stabilization service, especially on the frequency side, could also be used as a revenue model for the end user. One thing that's also often forgotten is the fact that a lot of stacks are still at a relatively low voltage. So you see stacks at 400 volts, 600 volts, 800 volts. From an electronics perspective, the efficiency of the conversion is simply the highest at the higher voltage. And it's limited by the low voltage directive. So ideally, you would have a stack at 1500 volts. And eventually, we'll get there. So now imagine you're investing into a large hydrogen facility. And 6, 8, 10 years down the road, your stack is worn out. So you will have to replace the stack. And by then, we're, let's say, 8 years from now, there's a lot of innovation that will have been done in the intermediate time. So you would probably want to replace your old stack by the newest stack, and that's probably at a higher voltage. If you don't take into account that you will have to have a converter that is capable of operating at that higher voltage rate, you will need to replace your power electronics as well. So you will need to think about having a good DC output range already now, because simply physics demands that you have, for example, a certain range between the different current carriers. Otherwise, it will simply not work. So if you don't take this into account right now, making your installation future-proof, you're making a mistake that's going to cost you dearly at a later stage. Now also, this is often seen as a minor point, but size and footprint matters. First of all, if you have a smaller installation, you're losing less material, so you have a lower supply chain risk and a lower cost basis. But a lot of the projects, they are based not in northwestern Europe, but in the desert in Namibia or in Australia or what have you. So transportation to site where infrastructure is poor is going to cost a lot. And simply by having a smaller footprint, your transportation costs go down. Same goes for the ground foundation preparation. Sure, the ground in the desert is cheap, but the preparation of that ground isn't. So you have to take that into account, and the same goes for installation and commissioning. And in very special cases, for example, when integrating hydrogen at sea is, of course, a topic. Yeah, the less space you need, the more cost you save there as well. And as the fact that for service, things do break eventually. You'll need to service it. So again, having smaller modules will help you a lot in that case. So now, if you look at the semiconductor technologies that are available, there are actually three. Two of them are now incumbent. So something that's already been used since the 70s, very old technology, is a thyristor-based technology. It's a passive solution. It basically switches more or less at the same frequency as the grid. So whatever happens on the grid, you can't do a whole lot, but just dissipating energy. And the power density at system level, so if you take into account all the filters that you need to apply to have this nice sinusoidal waveform, it's pretty poor. So IGBTs are a big improvement already. They're mainstream since the 90s. They are offering an active solution. Switching frequency is already higher than the grid by an order of magnitude. And the power density is also already improved compared to thyristors by about a factor of 2. But since the last 5-6 years, and actually we've been using this since 2011, and it's quite commonly used technology. All electric vehicles, for example, are almost 100% based on silicon carbide technology nowadays. So in terms of reliability, very big steps have been made. It is again an active solution, and the switching frequency again is much higher than what IGBTs are offering. So again, this technology is much more agile in dealing with whatever the grid is throwing at you. And the power density is, if I look at the systems out there, easily a factor of 3, but I've also seen factor of 5, smaller than if you look at the total system based on thyristor-based systems. So the technology that we're using is basically silicon carbide. And we've come up with this system, which is very compact. Basically a 1 megawatt system is the lectern that I'm standing behind. That's everything, filters, all of it. THD is less than 3%, so very scalable, all the way to gigawatt scale. Future-proof, so we give a very wide range of DC voltage, about 350 volt all the way to 1500 volt. And if you are expanding, it's simply adding modules to the racks that you have installed. You can basically parallel about 100 of these modules, so go all the way to 20 megawatts. And that way, use that as a building block for whatever stack you want to buy from whichever technology provider, whether it's solid oxide or alkaline or PEM, doesn't really matter. One point I also want to make, by the fact that it is modular, it's not just about the service, it's also about availability. And the fact is, if you have a monolithic system, it breaks down, you lose all your hydrogen production. If you have a 20 megawatt system with 100 of these modules, you typically lose 1%, not 100%. And finally, the fact that we are switching so fast leads to the fact that you can switch off and switch on modules as your load is increasing or decreasing. And that basically means that you can always work at your optimal conversion point. So the efficiency that you see here, peak efficiency of 98.7% over almost a complete load range from 5 to 100% remains more or less at that very high efficiency. And that is definitely a difference between the older technologies that I haven't seen out there yet. So if you want to, I'll skip this in light of time. If you're interested in further discussion, we're located just close by in booth B78. And I'm happy to discuss any points that I made more in depth at the booth in a more personal setting. Thank you very much.